Welcome to our deep dive into the fascinating world of dinosaur bone marrow analysis. Join me as we venture into the heart of paleontological discovery, where the secrets of creatures long extinct are revealed through the tiniest of clues. Today, we'll uncover how fast dinosaurs grew and whether they were warm-blooded or cold-blooded. These questions have puzzled scientists for centuries, but by examining the intricate details of fossilized bone marrow, we can begin to unravel these ancient mysteries. Prepare to be amazed as we journey back millions of years, using cutting-edge science to paint a vivid picture of dinosaur life, growth, and evolution. Our journey begins deep inside the bones of dinosaurs, within a substance called bone marrow. This remarkable tissue, often overlooked, is a vital component of the skeletal system, playing a crucial role in the life of these ancient creatures. This soft, spongy tissue might seem inconsequential at first glance, but it holds the key to understanding a dinosaur's life in intricate detail. Within its porous structure, bone marrow is a powerhouse of biological activity. Bone marrow is the lifeblood of the skeletal system, responsible for producing the blood cells that course through a dinosaur's body. These cells are essential for carrying oxygen, fighting infections, and clotting blood, making bone marrow indispensable for survival. But it's not just the marrow itself that's important. The surrounding bone structure provides a treasure trove of information. The bones act as a historical record, preserving details about the dinosaur's growth, health, and even its environment. Imagine, if you will, the growth rings of a tree. These rings tell the story of the tree's life, from periods of rapid growth to times of hardship. Just like these rings record the tree's age and growth spurts, the structure of dinosaur bones reveals their own growth patterns. Each layer of bone tissue can tell us something new about the dinosaur's life. As dinosaurs grew, their bones grew with them. This continuous process of bone formation and resorption left behind a detailed record of their development. This growth often left behind distinct lines, much like the rings of a tree, called lines of arrested growth, or lags. These lines are crucial for paleontologists as they provide a timeline of the dinosaur's life. By analyzing these lags, we can determine how fast a dinosaur grew at different stages of its life. This information helps us understand the growth rates and life history of these magnificent creatures. The spacing between these lines tells a story of rapid growth spurts and periods of slower development. Each gap and line is a chapter in the life of the dinosaur, revealing its growth dynamics. And from this story, we can glean insights into a dinosaur's metabolism, activity levels, and even its potential lifespan. By piecing together these clues, we can reconstruct the life of a dinosaur, understanding not just how they lived, but how they thrived in their ancient world. These lines of arrested growth, or LAGs, are like a diary etched into the very bones of dinosaurs. Each line signifies a pause in the animal's growth, often linked to seasonal changes or periods of environmental stress. By studying the spacing and frequency of these LAGs, we can determine whether a dinosaur grew continuously throughout the year, like many warm-blooded animals, or if its growth was more sporadic, like that of cold-blooded reptiles. The presence of lags in dinosaur bones has sparked a heated debate among scientists. Were dinosaurs warm-blooded or cold-blooded? The answer, it seems, lies somewhere in between. While some dinosaurs, particularly the larger ones, exhibit lags that suggest periods of slower growth, their overall growth rates were remarkably fast, more akin to warm-blooded animals. This suggests that dinosaurs may have possessed a unique physiology, unlike anything we see in the animal kingdom today. Some scientists believe that dinosaurs may have exhibited a form of mesothermy, a metabolic state somewhere between warm-blooded and cold-blooded. This intriguing possibility opens up a whole new window into understanding the physiology of these ancient creatures. Let's turn our attention now to the astonishing growth rates of some of the most iconic dinosaurs. These magnificent creatures, which roamed the Earth millions of years ago, exhibited growth patterns that continue to baffle and amaze scientists today. Take, for instance, the mighty Tyrannosaurus rex. Known for its fearsome appearance and formidable hunting skills, the T-Rex is a prime example of rapid growth in the dinosaur world. This apex predator could reach its colossal size in just a couple of decades, a feat rarely seen in the animal kingdom. From a hatchling that could fit in the palm of your hand, it grew into a giant weighing several tons. Imagine a creature growing from the size of a small dog to a bus-sized behemoth in such a short span of time. This rapid growth is not just impressive, but also indicative of the unique biological processes at play. This incredible growth spurt required a tremendous amount of energy and resources, suggesting that T-Rex possessed a highly active metabolism. Such a metabolism would have necessitated a constant and abundant food supply, making it a relentless predator. But it wasn't just the carnivores that grew at astonishing rates. Herbivorous dinosaurs, too, showcased remarkable growth patterns that allowed them to reach enormous sizes. The massive, long-necked sauropods, the largest land animals to ever walk the earth, also exhibited remarkably rapid growth. These giants could grow from tiny hatchlings to towering adults in just a few decades. These gentle giants started their lives as small, vulnerable hatchlings, but within a few short years, they would tower over the prehistoric landscape. Their rapid growth was essential for survival, helping them avoid predators and compete for resources. Their bones bear testament to this incredible growth, with elags spaced closely together, indicating rapid and sustained development. These growth rings, much like those in trees, provide a window into the life history of these ancient giants. Even smaller theropods, the group that includes Velociraptor and its kin, grew much faster than their reptilian counterparts. These agile predators needed to grow quickly to become effective hunters. This suggests that a higher metabolic rate, perhaps even warm-bloodedness, was more common among dinosaurs than previously thought. Such metabolic traits would have given them the energy and endurance needed to thrive in their dynamic and often harsh environments. The question of whether dinosaurs were warm-blooded or cold-blooded has captivated scientists for generations. This debate is not just a matter of curiosity, it has profound implications for our understanding of dinosaur behavior, ecology, and evolution. Warm-blooded animals like mammals and birds maintain a constant internal body temperature, which allows them to remain active in a wide range of environmental conditions. This ability to regulate their body heat internally is a significant evolutionary advantage. On the other hand, cold-blooded animals, like reptiles, rely on external sources of heat to regulate their body temperature. This means they are often less active during cooler periods, and must bask in the sun to warm up. The evidence from dinosaur bone marrow points towards a fascinating possibility. Dinosaurs may have possessed a unique physiology that allowed them to regulate their body temperature more effectively than cold-blooded reptiles. This unique trait could have been a key factor in their dominance during the Mesozoic era. However, this regulation might not have been to the same extent as modern mammals and birds. Dinosaurs may have had a more intermediate metabolic rate which is neither fully warm-blooded nor cold-blooded. This concept, known as mesothermy, suggests that dinosaurs may have had a metabolic rate somewhere between that of warm-blooded and cold-blooded animals. Mesothermy would have allowed dinosaurs to be more active than cold-blooded reptiles, but without the high energy demands of warm-blooded animals. This would have given them an advantage in terms of activity levels and growth rates, enabling them to grow larger and move more efficiently than their cold-blooded counterparts, allowing them to thrive in a variety of environments. From lush forests to arid deserts, dinosaurs were able to adapt to different habitats, which contributed to their widespread success. The presence of elags in some dinosaur bones, coupled with their rapid growth rates, suggests that they may have experienced seasonal fluctuations in their metabolism. These lines of arrested growth indicate periods of slower growth, likely corresponding to colder seasons, slowing down during colder periods and ramping up during warmer months. This seasonal adjustment would have been crucial for their survival, allowing them to conserve energy when food was scarce. This ability to adjust their metabolic rate would have allowed dinosaurs to conserve energy when resources were scarce, while still maintaining a higher level of activity than their cold-blooded counterparts. This adaptability might have been one of the reasons for their long-term success, while still maintaining a higher level of activity than their cold-blooded counterparts. This balance between energy conservation and activity would have been a significant evolutionary advantage. The debate surrounding dinosaur metabolism is far from over, with new discoveries and technologies continually shedding light on this complex topic. Scientists continue to analyze fossil evidence and compare it with modern animals to better understand these ancient creatures. But the evidence from their bones provides tantalizing clues to their physiological secrets. As research progresses, we may one day fully unravel the mystery of dinosaur metabolism, offering a clearer picture of how these magnificent creatures lived and thrived. Our exploration of dinosaur bone marrow takes us now to a remarkable discovery that has revolutionized our understanding of dinosaur reproduction: medullary bone. This specialized type of bone tissue found in female birds during egg production was thought to be unique to avian species. However, in a groundbreaking discovery, scientists identified medullary bone in the fossilized remains of theropod dinosaurs. This finding sent shockwaves through the paleontological community, providing definitive proof that dinosaurs, like birds, laid eggs. But the significance of medullary bone extends far beyond confirming dinosaurs' reproductive strategies. The presence of medullary bone in young dinosaurs, some of which were not yet fully grown, indicates that these animals were reproductively active at a very early age. This discovery challenged the prevailing view that dinosaurs, like many reptiles, had long lifespans and reproduced slowly. Instead, it seems that dinosaurs may have adopted a more bird-like reproductive strategy, reaching sexual maturity relatively quickly and investing their energy in producing multiple clutches of eggs throughout their lives. The discovery of medullary bone in dinosaur fossils highlights the close evolutionary relationship between dinosaurs and birds, further solidifying the link between these ancient creatures and their modern-day descendants. Thanks for joining us on this incredible journey into the past. We've delved into the microscopic world of dinosaur bone marrow, uncovering secrets about their growth rates, metabolism, and even their reproductive strategies. What dinosaur do you think grew the fastest and why? Let us know in the comments below. We love hearing from you. Was it the mighty Tyrannosaurus rex, the towering sauropods, or perhaps a smaller, more agile theropod that surprised us all? Don't forget to like, share, and subscribe for more fascinating insights into the world of dinosaurs. Until next time, keep exploring the wonders of the prehistoric world and stay curious.